Hello, this is Christian Cruz. I'm partnered with Abner Beltran. This is for our final project on class CE6370. I would like to begin with discussing the hard processor and its C application. The first feature that I had implemented for the hard processor was the user-provided plain text as well as the randomized encryption keys. So to do this, I figured it was abstract enough from the hardware such that I could probably test this on a local PC. That way I won't have to worry about file transfer and therefore I could iterate quicker and have more testing and verification runs. So to facilitate this, I made simple modifications to the build system such that it would accept a variable called build. So this is simply just a build flag where I can select whether to build for the host PC, that is my local computer, or to cross-compile to run it for the FPGA. So once I developed far enough such that where I found the logic and behavior to be satisfying enough on my PC, then I would make sure that it was compatible to run on FPGA. And this allowed me to successfully implement both of those features. So to randomize the bytes of the encryption key, I utilized a file called dev.urandom. This is a file that's already available to you in the Unix environment. As for the user-provided plaintext, it expects a format of each hex byte, or a total of 16 hex bytes, separated by spaces or new lines. Now, the assignment had given us the routines necessary for performing the actual encryption in software. The idea being that we would implement decryption and we would have a golden reference to compare to for when we would decrypt the ciphertext from the FPGA. So I had to implement the decryption process. That way I can have a golden reference for later verifications when integrating with the FPGA. Personally, I myself am not well versed with the AES specification, so I went ahead and utilized AI assistance with Microsoft Copilot to help implement these routines. So it managed to utilize some of the routines from the forward encryption process that were given to us, such as the key expansion function and the add round key function. And essentially what the entire process is doing is that it's undoing the process from forward encryption. So for instance, inverse shift rows is undoing the process of shift rows, respectively. And essentially what it's doing is that it's utilizing inverse matrices to undo the mathematical operations from encryption. That said, I was able to successfully decrypt the ciphertext that was produced in software. So now you can see at the bottom of the screenshot provided here that the decrypted ciphertext matches perfectly with the user-provided plaintext. I will now pass it off for the FPGA section.
Hi, my name is Abner Beltran. I'll be covering the hardware side in the FPGA in Quartus project section. So, starting off with the AES encryption, we'll get the input from HPS that includes the encryption key, plaintext, and a separate control variable, AES start, to let the FPGA know that it's ready to start the AES encryption. So, we'd get that through the AXI interface, and then we'd pass that on to the AES separate Verilog module, which is instantiated inside our GHRD top, which is how we communicate with the HPS. So once we are able or get a post start, then it goes through remaining logic, which includes the finite state machine, the AES encryption or the combinational round logic, and that would output the ciphertext, which would then get sent to the HPS. So here on the right, you can see some of the FSM and combinational round logic that we used. Once we get a post start and it's not busy, otherwise we are in the first round, it would set the plaintext and the key to the corresponding variables, which would then get sent to the combinational round logic, which is where it begins the substitution, the shifting rows, and the mixing columns. That's only for the first round. Technically, it also encompasses the busy, which is when we are not starting anymore and it's already going through the round logic. But once it reaches the final round, it will send a done signal, and that's just to let the HPS know that it's ready to read the ciphertext. Some of the PIO peripherals that we used include the encryption key that we had to make in the platform designer, the plaintext, and the ciphertext. We had to split it into four 32-bit segment since the max width bit of the PIO peripheral is only 32 bits. So that corresponds to the key 0 all the way to key 3, and the same for plaintext and ciphertext. The key and plaintext were the inputs from the HPS. We sent the ciphertext as an output to the HPS, and the other control signals I mentioned before, PIO done, just to let the HPS know that the AES encryption process was completed and it's ready to read the ciphertext. The other one was the AES control, which was again to let the FPGA know that it has received the encryption key and the plaintext from the HPS and it's ready to start the AES encryption. So the base addresses that we used were increments of 10. That way we didn't have any overlap, and that was sent to the header file or the HPS0, I believe, just to let the um, C code know where the memory mapped addresses were. We synthesized the report, and these are the resources that the FPGA used. Originally, we intended to do the AES encryption process inside the top file, the GHRD top. Unfortunately, it let each pin be known as a separate pin, thus we had more pins than we needed, and the FIDO report didn't synthesize. So we had to create that as a separate Verilog file, which we then used internal wires and instantiated that inside to be able to have the GHRD top synthesize. That way we don't have as many pin usage that wouldn't let the report or the HDL synthesize. We didn't have any constraints in the ALM register or RAM block, so the report used as much as it wanted, and we did only have the one constraint with the clock, so the max frequency, the minimum was going to be the 50 megahertz, so we were able to meet that. This is a test bench simulation, which shows the AES 128-bit standalone Verilog file showing that it works. Um, you can see the known key and plain text that were hard-coded in the Verilog file. We sent a post cert, which then started the AES encryption. Once the AES encryption was done, it would send the done signal back. This is the simulation result at the bottom, which you can see matches the expected ciphertext, showing that the encryption works. You can see the AXI interface here. The PIO external connections are what we connected to the internal wires in the GHRD top, which would then get sent to the AES. PIO peripherals would be what connected to the PIO external, and that would also connect to the lightweight HPS to FPGA AXI bridge, which connected to our HPS. That concludes the FPGA in Quartus project section. I'll pass it on to system integration.
Now that we have discussed the implementation of the hard processor and the FPGA as individual components, now we'll start trying to tie them in and integrate them together as a working system. So here's a sequence diagram that I have provided to help convey the actual design of each step of the intercommunications of both components as well as the user. So you can see here the user provided a plain text, the hard processor will generate the randomized encryption key and produce the encrypted ciphertext as a golden reference. It would then write a plain text encryption key to the FPGA's input memory addresses. This is referring to the PIO variables and values that we're utilizing to share information with the FPGA. And then we will raise a bit. That way we can actually send some kind of event to the FPGA to let it know that the plaintext and encryption key are ready for use. So that's when the FPGA will perform the encryption process, and when it is done, it will raise this PIO done bit. So in this point here, this is when the HPS has been waiting on the FPGA. So once the PIO done bit has been raised, the hard processor should be able to see that and will then read the ciphertext to then begin the decryption process there afterwards. That is our ideal case. So here's what is actually happening. This is a screenshot of the console output that is demonstrating the hard processor to FPGA interaction and communication. So here what you see are some extra debugging statements that were used to help verify and confirm that as soon as we were to write to a address, we would read it back immediately to confirm its contents are being updated as intended. So for instance, here at the top, we're intending to share the key by writing to the address of the PIO. So this is our encryption key that we intend to write, and then right afterwards we would read them from the FPGA. So that helped confirm that we were writing successfully, and therefore the inputs to the FPGA's process is being satisfied. Process repeats with the plain text, and then we set a bit to indicate that the input from the hard processor to the FPGA is being ready for use, and therefore the FPGA should be ready to begin encryption. However, we have been struggling with actually producing an encrypted ciphertext from the FPGA. However, does this confirm that we can write to the FPGA from the hard processor successfully? To verify that we can read from the FPGA to the hard processor, I went ahead and configured the the first 32-bit word of the ciphertext output from the FPGA to have a default value of our classic dead beef. So initially, our prior testing just left the reset default value of 0. So I was concerned that I would need a way to distinguish whether we can actually read from these output PIOs from the FPGAs. So I went ahead and modified that, and I have confirmed that we can in fact read from the FPGA. So input and output reading and writing between the hard processor and FPGA functions successfully. And so here I modified the print statements, removing the excess debugging print statements from earlier to satisfy the format of the assignment instructions. So here we have randomly generated encryption key. It is different from this run because the encryption keys are randomly generated unique every single runtime. This plain text corresponds to what's provided with the user. So this was from the example that was given to us. This is some random input that I had provided. And then we have the ciphertext and the decrypted plain text on a hard processor, just to demonstrate that we do have the decryption process working successfully. And here is the ciphertext that we'd received from the FPGA, although it's not matching expected to what we had been looking for. And for that reason, we do not have a decrypted plain text from the FPGA. I will now present the project with a demonstration. Hello, I will now commence the project demonstration. So let's just have some pre-written sample values for the plain text. I've already cross-compiled and transferred my executable to the FPGA target device. I'll provide the value for the plain text, and you can see that it's being read correctly here, and the software generated ciphertext is successfully decrypted back to the user provided plain text values. You'll see here that we are unable to produce a good ciphertext from the FPGA, and therefore we do not have a plain text that we can produce out of that. So we have this issue persists despite the FPGA having been confirmed to successfully perform the AES encryption process through a test bench simulation, as well as despite having confirmed the reading and writing operations working successfully between the hard processor and the FPGA. So this means that there may be some kind of disconnect somewhere with how the synchronization variables, signals, variables, and data is being passed around with potentially the Verilog files that are using the AES module and integrating it with the PIO at a higher level. Who knows? I suspect that it's something very small, and I feel that we are very close. Now we can test this with another value that I had pre-prepared for the sake of time. And there you go. The user provided plain text is here, read successfully, decrypted successfully On the hard processor, we're still seeing the default value of dead beef that had set for a reset value. If we want to check again to see that the encryption key is being produced randomly at every runtime, oops, my apologies. You can see that the encryption key here, 650 BEC, differs with 736F, etc. And that concludes the project demonstration.